Okay, this video is about elementary transformation. These are things. These are ways you can change a matrix. So as a concrete example, let me have a matrix. You can change any matrix. It may not be a square matrix. So let's say I have a 3 by 2 matrix. 1, 2, 3, 4, 5, 6. This is a 3 by 2 matrix. So there are various ways I can change this matrix. I can transform this matrix. So the first way to transform a matrix is to interchange any row. Interchange two rows to be specific. So I can choose any two rows and I can swap them. So the notation is let's say I want to swap the first and the third row. So one way to denote that is R1 with a double-headed arrow going to R3. So this is one way of denoting that you are interchanging rows 1 and 3. Another way of denoting this is R13. This is not 13. This is the notation for interchanging two rows, one and the first row and the third row respectively. So when I do this, the resultant matrix that I get is this. So if I interchange the first and the third row, the first becomes the third row. So this 1, 2 goes to the third row. This 5, 6 comes to the first row, and then everything else remains the same. The second row remains the second row. It doesn't change. So this is what you get when you interchange two rows when you do this elementary transformation. Of course, this is a different matrix. So when you do elementary transformation, you end up getting a different matrix. But don't worry about this. You'll see in later part that we don't lose much information regarding our original matrix. Our original matrix is somehow hidden in this new matrix. We will see about it a bit later. The other kind of transformation that you can do is this. You can multiply by a scalar. You can multiply a row by a scalar. As you know, a scalar is just a number, and here it has to be a non-zero. It has to be non-zero scalar. So let's say I want to multiply this first row with let's say 9. So the one way of denoting this is 9 times my first row. So first row I'll denote it with a R1. So this is the transformation that I am applying on this matrix. So when I apply this transformation, what I get is the first row gets multiplied by 9. So the first row gets multiplied by 9. First entry becomes 9 into 1 is 9. Second entry becomes 9 into 2 is 18. Everything else remains the same. It stays 3, 4, 5, 6. So yeah, this is how you denote multiplication by a scalar, a non-zero scalar to be specific. Another way of denoting this is this is a very uncommon way. It says R1 changes to 9 times R1. This is you might see some people denoting this in this way, but this is very common notation for multiplying a row by a scalar. Here 9 in this case. Again, you are getting a new matrix, but your original matrix is somehow hidden in this new matrix. We'll see about it a bit later. The third type of transformation is you can add a row to another row. A row to another row. And this addition will be done term by term. So let's say I want to add the second row to the first row. So one way to denote this is that I want to change the first row, right? Because I'm adding the second row to the first row. So I have my first row written first, and what I'm adding to it is the second row. So I add R2 to it. So this is the way to denote that you are adding the second row to the first row. And another notation is that you are starting with the first row, but it gets transformed to the addition of rows 1 and 2. So this is very clear that here you have the first row being changed. It is being changed to R1 and R2. Here it's a bit unclear whether you are changing the first row or the second row, but convention says that you are changing this first indexed row. So when I add the second row to the first row, uh, I get a 3 added to a 1, so that becomes a 4. I get a 4 added to a 2, so that becomes a 6, and everything else remains the same because we are not changing anything else. We are just changing one row at a time. So everything else remains the same. So this is the third type of transformation. Now I know in some reference books, in some textbooks, you might see that the third transformation is not just addition of a row; it is addition of a scalar multiple. Addition of a scalar multiple of a row to another row. A row to another row. So one example of this is that let's say you have a 7 times the second row being added to your first row. So you are starting with your first row, and you are not just adding one copy of R2. You are adding 7 copies of R2. They say this is one kind of elementary transformation, but I don't think this is something new, because this can be achieved by a sequence of some of the previous transformations. Precisely, what you are doing here is first you are multiplying the second row by 7, right? So you can first do this multiplication of a row by a scalar. So I can do a 7R2 first, and then now my new R2 is 7R2. So my R2 gets changed to 7R2, and now I can add this to my first row. So my first row can be changed to R1 plus R2. So here it might seem like I'm adding just one copy of R2, but now my original R2 is 7 times R2. So this is essentially adding 7 copies of my original R2, the second row, to the first row. And since I have changed my second row, which I didn't intend to, I can again revert it back. I can change my second row to original. So if I multiplied it by 7 earlier, if I want to get it back, I'll multiply it by the reciprocal of 7, that is 1 by 7. And if you do these three transformations in this way, in this sequence, it's as good as this one transformation. And let's just for kicks, let's do this on this matrix. So I have 7 times my second row. So let's say I have a temporary row stored somewhere. 7 times my second row is 21 and 28, and I'm adding this to the first row. So if I add it to the first row, this becomes 29, and I'm sorry, not 29. 21 added to a 1 gives you a 22, and 28 added to 2 gives you 30, and everything else remains the same. This remains 3, 4, 5, 6. So this is the way of doing it in just one step. The other way that I showed you here is this. It involves 3 steps. So what you do is you multiply the second row with the 7 first. So first you get uh, 21, 28, and everything else remains the same. 5, 6. Then you add the second row to the first row. So now essentially I am doing what I was supposed to do earlier. So 21 added to a 1 gives you 22. 28 added to 2 gives you 30. And everything else remains the same. So this 21 remains 21. This 28 remains same. 5 and 6 remains same. But to get this matrix, I didn't have to change the second row, right? I had to have 3, 4 as my second row. But this is 21, 28, which was the result of being multiplying it by 7. So if I want to undo this, I'll need to again multiply it by 1 by 7, the second row. So this becomes 3, 4, and everything else remains the same, 22, 30, and 5, 6. So this is kind of the 3-step process, but this is just one step process. It gives you the same result, but this is kind of very elementary. It involves doing multiple elementary transformations one after the other. So the very first essence from this is that all these transformations, they are invertible in the sense that you can undo them. For example, the very first transformation that we did here was interchange row 1 and 3. So if I were to undo this, I would just do the same transformation again, right? So if I had my original matrix to be this, I did this transformation row 1, 3, and if I were to undo this, I would just do this again on the resultant matrix. So if I were to now interchange 1 and 3 row, I would get 1 goes 1 and 2 go to the first row, 5 and 6 go to the third row, and everything else remains the same. And you can see that I've actually got my original matrix back. So you can see that my original matrix is somehow hidden in the new matrix that you get, but it can be achieved by using some transformations. Basically, the transformations involving undoing your the transformations. Also here, if I multiplied my first row with 9 to get my original matrix, I can simply now multiply it by 1 by 9. So I can multiply it by 1 by my scalar. Now this is the reason why I insisted on the scalar being non-zero, because if I were to multiply it with a 0, then to undo it I would have to multiply it by 1 by 0, and 1 by 0 is not defined. So that's the reason I had to have a non-zero scalar. But if I multiply it with 1 by 9, the first row with 1 by 9, this 9 becomes a 1, this 18 becomes a 2, everything else remains same. So 3, 4, 5, 6, and yes, you can see this is my original matrix 1, 2, 3, 4, 5, 6. And lastly, to undo the addition of another row to the first row, I can undo it with subtraction. I can change, I can do it R1 minus R2. Okay, so to undo the addition of one row to another row, you can just subtract the second row from the first row. So if I subtract 3 from 4, I get a 1. If I subtract 4 from 6, I get a 2, and everything else remains the same. 3, 4, 5, 6 remains the same. So yeah, I do get my original matrix back. So you can see my original matrix is somehow hidden in the new matrix. It's not completely lost. The other thing to notice, to inform you about here, is that you can do all of these with columns as well. So you can interchange two columns just like you are interchanging two rows. You can multiply a column by a scalar, of course non-zero, and you can add one column to another column. Uh, but the thing you can't do is jumble the rows and columns. So you cannot interchange one row with one column, or you cannot add one row to one column. So that's not an elementary transformation. And I would suggest don't bother about doing elementary transformations regarding columns. Just stick to doing elementary transformations regarding rows. So we'll henceforth we'll only talk about elementary row transformations. And you'll realize that in the course that we are doing, everything that we want to achieve can be achieved just by row transformations. We need not bother about column transformations. Another very important property regarding elementary transformations is as follows. Let's say you have two matrices being multiplied. So let's say you have A, B multiplied, which gives you a matrix C. So a best way to do this is through an example. Let's say you have a matrix a 2 by 2 matrix 1, 2, 3, 4. And let's say you have B as a 2 by 1 matrix, let's say 4, 5. And since you are multiplying a 2 by 2 matrix with a 2 by 1 matrix, the result will be a 2 by 1 matrix. And the entries will be 1 into 4 plus 2 into 5. That's 4 plus 10 is 14. And 3 into 4 is 12 plus 4 into 5, 20 is 32, I guess. Yes, so this is a matrix multiplication. The thing about elementary row transformations is this. If you do some transformation, some elementary row transformations on this A matrix, so let's say I do this transformation. I add the first row to the second row. So I do this transformation R2 plus R1. So this matrix will change. So let's say I get a new matrix A bar. Let's say I get a new matrix A bar, which is what I get after doing this transformation. So I'm changing the second row. So my first row remains just 1, 2. I'm adding the first row to the second row. So this 1 plus 3 becomes a 4. 2 plus 4 becomes a 6. And I don't change this B matrix. Let's say I have just B. And now let me do the same transformation on the right hand side with the C. So if I were to change the second row, I would keep the first row intact, and I would add the first row to the second row. So if I add 14 to 32, it becomes 46. And let's say this is my new matrix C bar. And what you'll realize this is, if you multiply A bar with B, you will indeed get a C bar. So you can check it for yourself. 1 into 4 plus 2 into 5 is 14. and 4 into 4 is 16, and 6 into 5 is 30, which indeed gives you 46. So this is not magic. This is not magic. This is just the property of the row transformation. So in short, what it says is, if you do some row transformations on both sides, the equality is still maintained. So if I were to do some row transformations on the rows of A and the same transformations on the rows of C, then I would still be equal. So this equality is maintained. This is very important property. Is something you'll realize when we do the applications of row transformations to find inverse of matrix. We'll do that in the next videos.